Hey, Kansha, how are you doing? All right, looks like we've got some folks that have joined up. We will start momentarily. Hello, Kelvin. Hello, Alessandro. Hello, Horace. How are y'all doing? Alessandro, how's Container Days doing? How's it going? I'm seeing some of the tweets coming out of Container Days. I'm seeing Dotan tweet all the selfies all over the place. Looking like a good time there. I kind of wish I was there, but you know what? It's all good. You're there. You're doing your thing. I'm excited. I heard that Container Days is probably one of the largest events out in EU, so it's pretty cool. Yeah, I'll bring you up. And hello to everyone. Welcome, welcome. We're gonna be getting started in a moment. Alessandro, how you doing?
Oh, good. I'm at the booth. I saw your Twitter space coming up. It's still pretty packed. The conferences usually the last days they tend to go down in energy, but the energy is pretty high still. There were a bunch of raffles. Can you imagine how many people were around the booth for the raffles? Still going strong.
Oh, that's awesome. This is day two, if I'm not mistaken, right?
Yeah, and it's karaoke
Oh,
day, of course. So tonight
oh,
looks like it's a karaoke time tonight.
that's awesome. I'm jealous that I'm not.
You know that, right? So you not.
Oh yeah.
All right.
With Leanne involved, karaoke's happening.
Yeah, but yeah, good time. Met a lot of interesting folks. Awesome presentations, especially the one from George Castro, CNCF ambassador and developer for CNCF. So I strongly suggest you look it up when they publish the talks. And in general, like a great vibe, and of course, like Tolkien service mesh at this solo booth all day long. And tomorrow, my workshop on ambient mesh as well. So lots of stuff.
Oh, fantastic. Yeah, you know what? I'm glad you brought that up because we will talk a little bit about ambient mesh today in the context of service mesh. So, welcome everyone. My name is Marino. Alongside, I have Akansha Priya, who is a part-time DevRel in the open source space and works for We Make Devs. Akansha, do you want to go ahead and introduce yourself? And I think you're leading the space. I'm just here to kind of answer the questions. You're the interviewer. I know we've got Alessandro here who can also field some questions too, but Akansha, go ahead.
Hey everyone, hi Marino, hi Alessandro. So I'm Akansha and I'm currently, as Marino said, working as a DevRel at VMake Devs. And today, like last week, we had a space about introduction of cloud native networking landscape, and today we're gonna deep dive into service mesh, and I'm really looking forward to the space and I'm pretty sure that whosoever is attending this space, they will gain a lot of insights into it. Should I like start with an overview and
Yeah,
then I
go for it.
can?
Go for it.
Okay, so like if I start with a basic overview about service mesh, I would say that we have like got a ton of functionality, right, built in right into Kubernetes. We have got a CNI plugin, services, ingress objects, and gateways. And these are all tools that provides us with just so much power and capability from a networking standpoint. However, if you have worked with these objects before, you know that there's a ton of complexity that comes along with it. At a small scale, it might be manageable, but once your application scale or you are running multiple applications in your cluster, it's very quickly turns into a huge mess. So now, like you can imagine your boss is hammering you about security. Do you really want to go back and instrument every single service and object you wrote with mutual TLS? I'm pretty sure not. And we already know that manually creating certificates and getting them signed is a pain. So let's assume you did that. How likely are you gonna get it all right in the first attempt? And now you're going to have to type in the OpenSSL commands countless number of times and have countless terminal windows open just to figure out what you configured wrong. And believe me, this isn't something that it will take just a few hours, it might even take weeks. So, wouldn't it be amazing if you could just flip a switch and inject a proxy in every pod that did the mutual TLS automatically for every single outbound connection and on the other side for everything that comes in? So this is where service meshes really shine and pretty much act as a savior from a networking perspective. And they give you mutual TLS, which gets implemented automatically. They provide communication matrix, policy traces, fault injection, chaos support, and advanced traffic management capabilities. So this is what service mesh brings to the table, and there are a bunch of them to choose from. So some of the popular examples of service meshes that are used in huge production grade systems include Istio, Console, and Linkerd. So yeah, so this is like a high level overview of service meshes, and I'm looking forward to chat with Marino and Alessandro and to deep dive into this conversation. Also, a quick reminder, if you have any questions or thoughts during the discussion, please don't hesitate to drop them in the chat. We will make sure to address as many of them as possible. So yeah, over to you and Marino.
Awesome. Thank you so much, Akansha, for that overview. A service mesh is pretty key in a lot of strategies today, especially as you run various numbers of container deployments throughout your, let's say you're running multiple Kubernetes clusters. And the reason why service mesh becomes important is because of exactly what Akansha says. There is a need to be able to see what our services are doing. There is a need to secure the communication streams between these services and authorize them. And then there's also a need to be able to navigate to multiple different services through traffic engineering. So, why a service mesh? Let's dig into that for a second. Now, if you think about a monolithic application. A monolithic application is a single stack of code that does everything under the sun. Basically, it's your entire application in one big stack. And while that sounds great and all, you're keeping things consistent and things look clean, it's actually not the ideal approach, especially when you decide you have to make changes to that app, because guess what? You'll have to recompile it, and then when you recompile it, that means there could be some outages before people can actually access that new version of that app, or there could be some other constraints that you have to deal with. The fact that you have to recompile the entire damn thing is not practical. And obviously, we've evolved from those patterns and moved over to microservices because, as we know, with microservices, things come in very tiny chunks, which allow us to change these tiny chunks without affecting the main application itself. So, when you think about a service mesh for a second, what it's aiming to do is allow us to achieve that microservices connectivity, that microservices connection. So my monolith now operates as microservices, but all of these microservices need to call on each other, and they need to be able to do this either naturally in their own code base, or you use something like a service mesh to facilitate a lot of these communications for you. But let's just assume something for a second. You built everything with C++ today, and then you realize, because I'm moving away from C++ and I want to start leveraging, let's say, Go, a little bit of Python, a little bit of JavaScript, some Node, etc., maybe even some Java for some functions. Well, you can do that with a service mesh, because what a service mesh is meant to do is provide a layer that translates that call to another service that might be running a different language. So what that call is, it's a simple API or service call. It's saying, hey, I need to talk to this other service and capture some data from that service so that I can be able to process that data and provide some output to some other destination. So when you break up your application into smaller microservices, a service mesh allows you to use these microservices with different languages. So let's say your app is comprised of 4 microservices. Microservice 1 or service 1 ends up being built in Java. Service 2 is Go. Service 3 is Python. Service 4 is some other language like Rust. But it all feels like it's all on the same fabric, and they all can communicate with each other. That's not only what a service mesh is aiming to do. There's some other key components of what a service mesh offers. Now, like I mentioned, that there was one key reason around being able to build out distributed microservices, but the idea of observability, to know what our services are doing at any time, to understand, why they're misbehaving or not responding in a quick enough manner, is why service meshes exist. So one of the most important understandings or aspects of using or operating a distributed environment is understanding where latency might exist, where your errors in your request might exist, how much traffic is present across the wire, and for the number of requests that are flowing through, the requests per second that each service has to receive, and finally the amount of saturation. So let's give you a very quick example. I have two services, one service A and service B. Service A needs to talk to service B, but also there is a service C that also talks to service B as well. So service A and service C are using service B to capture some information. The challenge, though, is that service B can only respond to one of those, service A or service B, service C at any given time. Now, when it's answering service A, service C has to wait until service B responds and waits for it to process service A. But in that particular situation, it might be possible that the request that service C makes times out, and it might have to retry that request a few times until it actually times out. Now, this is a situation where your service is just overloaded, and because it cannot respond to requests, there's no mechanism in place today to buffer that request. So what a service mesh can do is it can actually tell services to wait, to delay the request, to hold on a little bit longer, just in case that service frees up, it has a cycle, now it can respond. Because if that were the case, if we tuned those calls appropriately and added that delay into the mix, then we are guaranteed to get a response. But if we don't add that delay, that artificial delay that we bake in or program into our app or our service, then chances are the app will error out and we won't get the response we expect. So Service Mesh implements this resiliency functionality that allows us to basically decide, hey, we're going to put a pause on the request, but once the cycle frees up, we'll process the request. Now, this is going to happen for thousands of microservices, and this is how you build resilient microservices altogether. You just want to make sure you implement the right timers after tuning it all to understand the correct flow and to make sure that, while latency might exist in your request flow, you're still able to get a suitable response in a reasonable amount of time. Now, where does the service mesh live? How does it look like? What is it doing? How is it deployed into an environment? Let's pick on Istio for a second, because Istio is the most widely used service mesh out there. It's been battle tested, it's used widely in production, and on top of that, you have companies like Solo that write abstractions to simplify your experience with a service mesh. So what is Istio? It's an open source graduated CNCF project that effectively provides service mesh functionalities across observability, security, and traffic management. But how it goes about doing this is it deploys Istio, something called an Istio ingress and egress gateway to control the flow of traffic into your cluster and outside of your cluster, and then also makes use of sidecar resources, what Akansha was mentioning previously, that attach themselves to your main application containers. Now, these sidecars are just mini proxies, or mini routers, you could say, that intercept any sort of service call and will process that service call according to any sort of rules that you've defined, any policies that you have in place, or any sort of traffic management engineering that you've decided to configure your services for. Now, what's really interesting is that the service mesh layer is a layer that sits on top of your network layer. It's not a replacement for your, let's say, CNI layer. Because guess what? When you deploy Kubernetes, you need to deploy a CNI. That CNI allows all the different pods in your cluster to communicate amongst each other. Or they need to communicate amongst each other. But they do so using IP and host name. But to be able to make some more intelligent calls and intelligent routing decisions and decide where to implement authorization, this is where that service mesh comes to play here. So you start off with a cluster, you deploy your service mesh. It'll go ahead and deploy an Istio ingress gateway, a control plane that goes on to manage your configuration for you, but also does something else. it passes along certificates to your workloads. So this brings us to another topic, identity and encryption within service mesh, and even authorization. So you have all of these services that have sidecars attached to them, and these sidecars are supposed to intercept every single request. You can program each one of these sidecars to look for attributes, specific attributes that either disallow or allow requests to be made. So say, for example, I have a service A that needs to run an HTTP GET request against service B. If you have a policy in place that is a default deny all authorizations, and then you have another policy in place that specifically or explicitly states service A can make an HTTP GET request method to service B, then that request method would go through. But if we did the reverse, if service B tried to invoke a request to service A, that would fail because of our default deny all that exists for the authorization. So this is how we control the flow of traffic. But then if we also wanted to implement some encryption, this is where the certificates come in, and this is where TLS comes in. So there's this concept of TLS, or transport layer security, which is a higher layer protocol. It's not a network layer protocol, it's an application layer protocol that effectively aims to verify the identity of an entity. So one way TLS is you have a highly secure resource that needs to be accessed. Now, in order to access that highly secure resource, you need to present that resource with a certificate. Your client host, let's say your laptop or your MacBook, is going to present a certificate to that highly secured application. As long as that certificate matches, then that application will allow you in. You'll be allowed to make requests, and you'll be on your way. However, if you don't present that certificate, well, guess what? You're not going to be able to make that request. Now, this is called one-way TLS because only one entity is authorizing and authenticating, I should say, authenticating the request. Now, there's a concept in service mesh called mutual TLS. It's two-way TLS where both ends, both the sender and the receiver, have to acknowledge and validate the identity of both ends. When you do that, you're ensuring that there is stronger controls and stronger identity in place because not only is the sender having to verify that they're sending the request out to a validated entity, the entity that's being validated also has to validate the requester. They have to make sure that this is a legitimate requester, much like in the traditional sense of me using my laptop to access a secure website. But on the flip side, because the requester also has to validate the identity of the service, this is also to prevent a situation where a malicious or nefarious service has made its way into your application stack and into your cluster, for example. So through that identity mechanism, now you've validated that these two endpoints are authenticated. The next step is to just encrypt the communication or the payload. So now if you try to sniff the traffic going between service A and service B, it's going to be jumbled, jarbled, garbled, whatever you want to call it, and unreadable because a certificate, a private public key pair, was used to encrypt the payload. And unless you have the private key on as the payload is moving around, you're never going to be able to decipher what is in that payload. So that's where the encryption comes from, and that's where identity is derived from as well. So it's interesting because when you think about service authentication, the same concept exists in cloud environments too. If you're familiar with AWS and IAM, or Identity Access and Management, it's a very, very similar concept where every single object in AWS needs to have a service identity attached to it, and that policy gets applied to the identity, not the object itself. But because you have applied it to the identity, now you can enact and enforce a policy against that identity since it's attached to an actual object. That's how all services operate within AWS. You can't simply just deploy EKS without all the sub-services trusting each other, because for the exact same reasons, you wouldn't want a malicious component making its way into your environment and compromising the integrity of both your infrastructure as well as the application. All right, pass it back to you, Akansha. Talked quite a bit.
Yeah, so thank you, Marino, for laying down for such a great foundation for service meshes. So building upon that, I have a question that there's a hot topic going around in the service mesh world about whether based approach to service meshes has a future, or if implementations such as Cilium sidecar-less approach using eBPF will soon replace sidecars. Like, what are your thoughts about this?
So there's already a movement to move away from sidecars, but it first begs the understanding of why. Why are we doing this? What is the importance of removing the sidecar? Now, there's always going to be a particular situation that you're in where sidecars actually hurt the situation and don't really help the conversation. There are situations where not having the sidecar actually does a disservice for the way you operate your environment. So let's understand the sidecar for a second. So when you deploy Istio with sidecars, for example, what ends up happening is you actually have to inject the sidecar into your already existing pod resource. So let's just say you deployed a simple application, I don't know, a simple hello app or something, and you decide you have to deploy the sidecar. In order to deploy that sidecar into that pod, you actually have to re-roll out the deployment to allow the Kubernetes admission webhook controller, or mutating admission webhook controller, to modify the pod resource and actually inject a new configuration, two configurations actually, one which is in an init container, and then the secondary, which is the sidecar proxy alongside the main container. So actually, when you look at the pod manifest definition, you'll see three containers. The first container is actually known as what we call an init container. That init container is responsible for redirecting the traffic from the main application container to the sidecar, where it originally goes to the network namespace directly and its local TCP/IP stack. Now, just a quick note, every network namespace is a pod. What is a network namespace? It's a mechanism to isolate and provide TCP/IP connectivity for processes. This is exactly what a pod is today in Kubernetes. Now, when you look at a pod is a single IP address. So, because it has a single IP address, one of the challenges is if you have multiple containers in that pod, how do you know which one you're communicating with? This is where port numbers come in. So every single container has a unique port number associated with it. So you'll say your main application container might be responding on port 8080, but the actual Istio sidecar resource is actually responding on a different port. I think it's like 15,021 or something like that. I need to go check the actual ports. But it's listening in for any sort of requests that are coming in from other sidecar resources or outside resources as well. So you have to manipulate using this init container first. And then when you manipulate that networking, the sidecar container handles all the inbound and outbound traffic towards that pod. So um, the reason I bring this up is because it's actually very intrusive at times to deploy and inject a sidecar, because that could result in your application going down and offline for a short period of time because you have to roll out a new deployment. So in certain situations with stateless apps, with the way they respond, this is okay. But for stateful apps, apps like SQL, for example, that don't work at HTTP but work at the TCP layer, have don't really gain any advantages for using a sidecar resource. There's also other situations where you have race conditions where the sidecar resource may not come online quickly enough um, for the application container. I mean, this has been resolved with a new sidecar KEP that was released in Kubernetes 1.27, where it actually treats the sidecar container as an init container, so it won't try to bring it online, or so it won't try to bring the application online before it brings the sidecar on. So in order to address this particular challenge and maybe address challenges around operational onboarding as well as resource reduction, that's a key point there, resource reduction. Well, this is where Cilium decided, okay, let's offer up a sidecarless approach. Just because they offered up a sidecarless approach, it doesn't truly mean that this is a full-blown service mesh. Because a full-blown service mesh, as I described earlier, offers three key things: traffic management, it offers observability, and a strong security and identity. But this is at a layer on top of the networking layer. So Cilium, while it does provide a sidecarless function, it still has to deploy an artifact like Envoy to operate as a daemon set to process ingress and egress traffic. While inside of the cluster, there is actually no concept of mutual trust. There's a concept of mutual authentication, which relies on validating the identities, but still has to use something like WireGuard or IPsec to encrypt the workloads. Now, WireGuard or IPsec are still okay replacements, but with IPsec, you have a challenge where IPsec has been known to be resource heavy and chew through a number of resources, both at the CPU and memory level, because of the encryption and decryption cycles and processing power it needs, but also the complexity side of it. And then on the other hand, WireGuard just doesn't have the FIPS compliance. So it's not a one size fits all. I mean, it's a suitable solution in certain situations, but if you're looking for the best of breed, you don't want to just use a CNI to do service mesh functions. You also don't want to use a service mesh to do a CNI function. You want to use both. Now, while Cilium deployed and created this sidecarless approach with using eBPF to optimize a lot of that traffic flow, Istio, on the other hand, decided to develop a sidecarless mode called ambient mesh. Now, with ambient mesh, the concept of the sidecar goes away in some sense. I mean, the sidecar functionality is still present. It's just not sitting right next to the main application container in the pod. So where does it go? What happens? Hold on a second. Let's get to that in a second. Now, if I have services that have not been intruded by with a sidecar, they can still continue to operate. And I can still onboard them into the mesh. This becomes extremely attractive to a lot of organizations that want to still take advantage of service mesh, but don't want the overhead of a sidecar or don't want the customization capabilities of a sidecar because they just are looking for simple things like TLS and layer 4 policy. So what happens with ambient mesh? If I remove the sidecar, where do I move everything to? So with ambient mesh, there are two main components that the sidecar was traditionally responsible for. Let's talk about that for a second. The sidecar is responsible for TLS or MTLS. It's responsible for any sort of layer 4 policy and connectivity. It's also responsible for layer 7 policy through authorization. It's also responsible for layer 7 observability. So things like tracing, understanding the X header ID or the B3 header propagation between services so we can capture a trace and know what spans live in that trace. This is all about distributed tracing, by the way. But that doesn't exist if I decide, okay, I'm going to drop that functionality and just drop sidecars. So inside of a service mesh, inside of ambient mesh, we have two components called the Z-tunnel and the waypoint. The Z-tunnel does a lot of the MTLS as well as some of the layer 4 authorization. So I can do layer 4 authorization and basically say services across clusters cannot communicate based off of these policies and these labels, and I can still have MTLS. But that Z-tunnel actually lives at the node level, and it's servicing multiple namespaces and service accounts. You can even scale the Z-tunnel resource because effectively it's like the sidecar. Now, I'm at layer 4 now, and maybe this is all I need for a lot of the operations. There might be situations where I need layer 7. If I need layer 7, I will strategically deploy a waypoint proxy close to the destination workload to basically process any sort of authorization at layer 7, any sort of HTTP request method at layer 7, any sort of observability that I need to capture at layer 7. And that's happening on an as needed basis as well. So when we think about that for a second, what are these proxies? So we have a Z-tunnel proxy and a waypoint proxy. The sidecar proxy actually was traditionally built and still is built with something called the Envoy proxy, a proxy that Netflix and Lyft and a bunch of other companies used, manipulated, built on top of, Istio built on top of it as well. And here we are today where Envoy is still widely used. But in order to cut down on the amount of CPU and memory utilization that we needed for Z-tunnel and provide it the speed that it needed, just push requests through and move packets really quickly, Z-tunnel needed to be rewritten. While it was using Envoy previously, it was rewritten in Rust to just support the key functions, layer 4 connectivity and MTLS. while the waypoint proxy still retained Envoy, which is fine. So now when you look at a comparison of 1,000 microservices running on a cluster, and you do them side by side, one running regular Istio and one running ambient mesh, you have one cluster that has 1,000 pods with 2 containers in each pod. So we have 2,000 containers running. And then we have a secondary cluster that has 1,000 pods. Each pod has only a single container. And then let's assume both clusters have 3 nodes. No, actually, no, that's a bad calculation because there's a max of how many pods you can run in a node. So let's just assume each cluster had 10 nodes, okay? So I would have 10 Z tunnels for the ambient mesh setup. And these Z tunnels would be a fraction of the sidecar, right? In terms of CPU and memory as a footprint. And then you have Istio on the other side, which is, you got sidecars everywhere. When you look at the memory and CPU comparison, and then you also marry that to the requests per second, what actually ends up happening is ambient mesh wins in a lot of those generic situations, stateless, for stateless workloads. And why that is because you have less devices, less hops overall, having to process traffic, and you have something that is very specific to just process layer 4 traffic. Overall, though, when you look at it from let's say we were looking at this from Grafana or some dashboard that tells us how much CPU and memory utilization we are consuming, well, guess what? You get to see that ambient mesh consumes less resources in total in comparison to Istio regular. But why this becomes attractive for a lot of environments, especially if you're running in the cloud cost is a huge concern, right? With cloud cost, your concern becomes, oh shit, I have all of these instances that are running and supporting my cluster, and I have to have this particular instance type to support the number of sidecars I'm running. Whereas if I'm running ambient mesh, maybe my cluster footprint has reduced, so my cloud costs get reduced as well. Let's look at the sustainability angle for a second. What is sustainability? Making sure that we are doing good for the better of our world, our environment, so that we're consuming less waste, or we're actually generating less waste overall, consuming less overall, and then just reaching a level of carbon neutrality, net neutrality for that matter. So when you think about ambient mesh, if I'm consuming less CPU and memory and less power overall, I am basically conforming to practices around sustainability as well. So to summarize, I know Siddhant asked the question, what is ambient mesh all about? So ambient mesh is a sidecar-less approach to service mesh, which offers up the exact same capabilities as the Istio service mesh, but at a lighter footprint. There are some trade-offs where you don't get the same level of sidecar capability because it's not existent anymore, but you still get most of the service mesh functionality that you normally would need. To answer your second question there, Siddhant, about an API gateway. So this is interesting. I'm going to talk about API gateways in a second, but before I do, I'm going to pause. If there are any questions or if Akansha has any thoughts, let me pass it back to her.
I did have some follow-up questions, but like if you want to talk about API gateways, we can go ahead with that as well.
All right, let's be quick about the API gateway story,
Yeah.
and then we'll also talk about gateway APIs and how service mesh fits into this. So before service mesh existed, actually service mesh has been around for a long time. Before it was widely used is what I really should say. API gateways were a pattern that were widely used. In fact, a lot of organizations still use them, and what API gateways pretty much do are act as the front door to your APIs or your services, whether they live in Kubernetes or they live elsewhere. Now, this API gateway, very much like what I described with the sidecar, intercepts traffic from the outbound and then has to process it with some policy. So what that policy might say is, when this request comes in, what information is in that request header that allows me to process this request in the most appropriate manner possible? Is there authentication in the header? Is there a special flag in the header that needs me to route this request to version 2 of the app? Is there a certificate presented? Is this a canary launch that I'm doing with this new service? there's a lot of, oh, am I rate limiting this request as well? Because I've received so many requests from this requester, I don't want to overload my request, so I need to rate limit it. Am I filtering my request because, one, my request is coming from a destination that is in my deny list, so I shouldn't allow this request to be processed. By the way, a request is just, a call. Anytime I say the word request, I'm making a call, a traffic call to a resource. So the API gateway is like a massive layer 7 down to layer 4 firewall, which also does things like rate limiting. It processes requests, it disallows requests, it will tag requests to point them to certain resources with certain flags. Now, this API gateway pattern was great, except what happens when we had services inside of our network that needed to have that same effect or take advantage of that same effect? Well, one approach would be to hairpin the traffic through the API gateway. And if you did that, it worked, except you're now overloading the API gateway with additional request processing. So to alleviate that, this is where service mesh comes in. It basically deployed mini API gateways as sidecars everywhere and basically achieved the same thing. Except now what you have is service mesh that does the API gateway functionality, receives traffic, will do the rate limiting, etc., and process requests appropriately. And then inside of your mesh, you have that same functionality as an API gateway, except you deploy them with the sidecars, or if you decided a sidecarless approach with the waypoints. Now, a quick note about the Gateway API. The Gateway API is a standardization. It is not an API gateway, just to be clear. The Gateway API spec is a standardization for Kubernetes where multiple providers standardize on the way you deploy ingress and the way you terminate TLS and route to different resources if you're doing things like a blue-green or a canary deployment. But it stops there. It's limited there because it only happens on the ingress side of things. Once you're inside of the cluster, if you have, let's say, services that need that same level of circuit breaking or traffic resiliency or traffic management or authorization, well, the service mesh is going to fit the bill with the sidecar approach or sidecarless approach. Now, having said that, the API gateway pattern strongly resembles what ambient mesh is doing. But ambient mesh strongly resembles what we used to do in traditional networking, where we had a perimeter firewall that processes traffic on the inbound, and then maybe we have a few firewalls for every subnet that we have, and we would process traffic for inter-subnet communication. Very similar patterns that we're seeing here, but to be very clear, a gateway API is the spec that Kubernetes has conformed to standardize on ingress and the way we terminate TLS, whereas an API gateway is a function that allows you to process your requests towards APIs behind it and provides a level of API management.
Thanks, Marino, for shedding light on the API gateway. So a little earlier in the conversation, you mentioned that sidecar proxies might not be the best fit for some scenarios. So could you please give some few examples where a sidecar proxy might not be the best choice? Also, adding on to that question, how do you assess the performance impact of using sidecar proxy in a service mesh?
Yeah, I touched on it a little bit, but let's take, for example, MySQL. Right, MySQL operates at TCP, so when you deploy a sidecar resource, anything that you do at this point has to be TCP based, meaning you lose a lot. You lose out on a lot with respect to the way a sidecar would actually function and process traffic at layer 7. And that's okay, right? We expect certain applications to not take advantage of the sidecar resource. A database is a perfect example of that. Anything that requires state are perfect examples of things that don't do well with sidecar resources. So if you decide you want to run a headless distributed database, well, if everything's operating at layer 4 and below, well, it makes no sense to use a service mesh. Because the one key interesting aspect of that is that you're thinking about the calls that you're making. You're making TCP calls. Even though Service Mesh understands this, there's no additional metadata that you can feed into your TCP request like you can at the HTTP level. You can't add certificates into your TCP request. You can't add authentication into your TCP request. You can't implement any sort of resiliency into your TCP request. You have to rely on TCP mechanisms altogether, things we cannot program. So in those situations, this is why you would not use a sidecar, and this is where ambient mesh fits. There might be other conditions where your application suffers greatly from that minimal latency that is added by a sidecar. So let's take, for example, high frequency trading. It's actually a lot faster for calculations to occur and output a stock ticker, valuation before a service mesh can actually even process the way these services communicate. Now, when you think about that, if stock prices have to wait on a service mesh to process policy and then pass along that traffic directly to the main application container and then flow back the other way, then you've actually done a disservice for high frequency trading, because they operate at not at the microsecond level, actually even I think smaller than that, at the nanosecond level. So when you think about that for a second, a service mesh doesn't do any justice to high frequency trading environments as well. And there are plenty other use cases as well where service mesh might not be the best fit, and or maybe a sidecar approach of service mesh might not be a best fit, but a sidecarless approach might be a good, excellent fit. Now, let's address the other challenge of resources, right? Let's say you're operating a highly distributed environment, and let's say your strategy involves edge computing. Now, as we know, edge computing can be an Intel NUC, it could be a little box, a laptop, it could be your own laptop, it could even be a couple of Raspberry Pis. Let's just assume we're using, a pair of Raspberry Pis that have, four quad cores each, have 8 gigs of RAM each, and are, connected to the same network, and we have a 2-node cluster. With 16 gigs of RAM, it's not a lot to give, especially if we have to load up our control plane. Let's say we decide we're going to use K3s, for the lighter weight functionality, and then we have to deploy ambient mesh on top. Once we've deployed those two, we might have enough resources to be able to run a few applications. But if we decided we didn't want to deploy a full-blown instance of Istio with sidecars for all of our apps, well, we've just lost about I think it's 0.2 megabits of RAM, and I can't remember the actual figures, but we've lost the amount of CPU and memory that for every sidecar we've deployed, meaning we can't deploy as many edge-based applications anymore. So there are some considerations around resource consumption and why ambient mesh might be an excellent fit for edge compute environments as well. So I hope that answers that question.
Yeah, definitely. So that was a great point. Thank you. So you talked about API gateways, and many organizations already use API gateways. So how can service mesh and API gateways work together to create a robust and efficient communication infrastructure? Are there any specific use cases where this combination shines?
Yeah, it's interesting that this was brought up, because imagine for a second you ran API gateways everywhere, and all of a sudden someone says to you, "Hey, why don't we do service mesh?" Well, are you going to rip every one of your API gateways out and then deploy the service mesh? No, that's not the right approach. You'd probably want to safe load your service mesh into your environment. But let's use Solo as an example, where they actually went through this transition period for a lot of their clients. So they had a huge client base that were already using Glue Edge, which was our API gateway technology built on top of Envoy. And when Service Mesh came along, well, how do we use Glue Edge with Service Mesh, with Istio, and maybe even Glue Mesh? Well, your two approaches here are, you can decide you're going to roll out a brand new environment and then do a live cutover to that new environment and drop your API gateways, but make sure that you can resemble a lot of the functionality inside of a service mesh. But wait, service mesh didn't have all the functionality of API gateways at the time, so you actually had to combine both. So one of the ways that allowed folks to onboard a service mesh while using an API gateway was actually to deploy a sidecar with the API gateway. This might not always be done, but this was an approach where now you have the API gateway a part of the mesh. Because it's a part of the mesh, on one end, it has a leg to the outside world, so it receives traffic, it ingresses traffic. And then on the other hand, the sidecar, because it has connectivity to other sidecars and it knows about sidecars through this service discovery, or the, what's it called? The service discovery service? Can't remember now. It's part of the XDS control plane in Envoy. But as part of that discovery service, or I think it's named discovery service now. Now I can't remember. Anyways, one of those discovery services effectively is telling the rest of the mesh, hey, here's the API gateway and it's receiving requests. Where can I forward on these requests to? Now, that's an approach where you can have these two coexist. But the reality is if we want to phase away the API gateway, something else has to replace it. So the Istio Ingress gateway effectively grew up to the point that it was able to do about, 75 to 80% of what Envoy was doing as a full-blown API gateway through Glue Edge. But Solo got smart and said, look, we can add the same level of functionality into the Ingress gateway that Istio provides that we were doing for Envoy, and nothing will be really different or that much different. It's just at the end of the day, your specific API gateway is no longer a separate instance, which was separately Envoy. It's now part of the Istio ecosystem. And so at Solo, we call this Glue Gateway alongside Glue Mesh as part of Glue Platform. But that's one way to solve it. There are probably a million other ways that I'll be completely honest about that I won't talk about, only because I know Leon is here, and Leon will call me out on my bullshit if I say anything. So, Leon, you're welcome to join up if you've got this cycles to just chat a little bit about service mesh. I also want to do a quick shout out to Amin. Amin, welcome. Thanks so much for showing up to this space. I also want to say that Amin did a hoot session recently on ambient mesh with Peter, one of our coworkers. So, go check out Amim and Leon and see some of the great stuff that they've been up to. All right. I hope that answers your question, Akansha. What else have you got for me?
Yes, so like one last question. So as we look ahead, like what trends do you foresee in the service mesh landscape? Are there any emerging technologies or practices that might shape the future of service mesh, API gateways, or microservices?
Yeah, there's a few things to consider, right? And a lot of this stuff is already starting to be done. So let's take eBPF, for example. For those that aren't familiar with eBPF, eBerkeley Packet Filter, it's a technology that actually allows you to write sandbox programs and operate them alongside the kernel. But these are safe sandbox programs. So they're not going to crash the kernel. If the program fails, the program fails, irrespective of the kernel. And because of that, the blast radius is very limited. And why this is attractive is when you think about Cilium as a CNI, Cilium actually uses eBPF to process traffic. How it does it is it actually has two components, a user space component and a kernel space component where the actual eBPF programs live. The kernel space component actually attaches itself to hook points and is looking for events, packet events. Hey, this packet is going to that in destination. Let's capture this. And they store that in a map, usually a hash map or a ring buffer. These are different ways to store data captured from the kernel. And then that gets translated into a user space application, which is what we see as Cilium. So an example of this is, let's just say I wanted to implement a firewall policy. I could do this with IP tables, but IP tables operates in software. Or I could do this at the kernel level where eBPF will intercept based off of that event and filter it accordingly. So it never, like, even though I see it in my user space, the action is actually happening at the kernel level. So, why am I even talking about this? Why is this even relevant? So we've already seen that eBPF can optimize traffic flow, but if we can use eBPF to optimize traffic flow for the sidecars, that means we actually will reduce latency between the sidecar resource as well as the main application container, which can be very powerful in situations for ultra low latency environments, much like high frequency trading, for example. I'm not sure if we're there yet, okay? But maybe we'll get there. Another advancement is Istio was always and heavily focused around microservices, containers. We assume that if you're going to run Istio, you're probably going to run Kubernetes. You're probably already running Kubernetes at this point. But there are situations where customers and clients and environments run virtual machines. You know, we don't want to discriminate and leave the virtual machines out of the picture. So how do we bring them in? In the last couple of years, Istio has spent a lot of, like the community in Istio spent a lot of time experimenting, evaluating, contributing to the code base so that VMs can be a part of the mesh. And this has already been achieved. So today, if you decide you wanted to have a bunch of VMs that were a part of your service mesh, you could absolutely do so. You basically would deploy a sidecar naturally inside of the operating system or the guest operating system of that virtual machine, and it would run as a process in Linux as well, and it would be an attachment into your service mesh. So let's just say you had a bunch of pods running in your cluster. They can communicate with each other, and they could also communicate with that virtual machine and pretend that it's in the cluster as well. So things like the traffic management that I talked about earlier will be available. Things like policy is still available. The observability piece is still there because it's a proxy that lives inside of your virtual machine. The real funny thing is, what I just described has been done for ages. Back when I started off my career in tech, one of the biggest themes was around VPN connectivity and even like implementing policy and where we would deploy proxies. These very same, or I shouldn't say very same, similar artifacts were actually deployed inside of our operating systems to just provide the same kind of functionality with what we see with virtual machines and service mesh today. So we've got two. We've got eBPF optimizations with service mesh. We've got virtual machines in service mesh. What else? Let me think. What's some of the other stuff that we expect to see? We already know that service mesh has some hooks into WASM. I'm not an expert on WASM, so I don't really want to talk too much about that. But one other interesting trend that you're going to notice is that a lot of big companies are going to gravitate towards using Istio either inside of their existing product, and I'm sorry I'm talking specifically about Istio, there's a reason why. They're going to bake this service mesh technology into their product and act as a subservice that we might not be aware of. Organizations are going to continue to drive their existing product strategy to have service mesh functionality that their end clients can consume. Example might be Tanzu Service Mesh or even Solos Glue Mesh, which has already been happening. We serve up an API and you can configure your mesh all the way through. But because of that, there's a strong possibility that ambient mesh, Istio Service Mesh has the potential to grow into a full-blown, full-stack networking solution. Meaning, if you think of Cilium started off as a networking layer that climbed up towards Service Mesh. It's possible that Service Mesh can climb down to the lower layers and provide networking. But again, this is a perspective and opinion. I can't say for sure if this is going to happen. I can't say this is a guaranteed thing. Now, if you really want to see what's going on in the service mesh space, there's a few areas you can go check out. Obviously, go to istio.io and take a look and see what they're doing. But also go to the GitHub repo and take a look at the issues. Take a look at the PRs. And you'll have a real good sense of what's being worked on for some of the newer iterations and versions of a service mesh. Here's another one. All service meshes are probably going to provide a conformance to the gateway API spec. Linkerd, Istio, Cilium, any other mesh you can think of will conform to that Ingress spec or the gateway API spec, which means that maybe we're simplifying the way we communicate with resources inside of our cluster. But the secondary nature of it is just to create a simple standard that everyone can use, right? Everyone can use across the board, so they don't have to battle with even though Istio Ingress Gateway is a fantastic starting point, if you are migrating from Linkerd to Istio and you're already familiar with Gateway API, that could be an approach. Now, here's the other thing, right? There is functionality that's lacking in the Gateway API spec that's not present inside of the Istio. That's present in the Istio Ingress Gateway is what I mean to say. So you might decide, hey, I need these additional features. I might go Istio Ingress. So there are some things to consider in terms of what's transpiring in the service mesh world. Yeah.
So thanks for sharing insightful thoughts, Marino. And I think we are running out of time as well. So thanks for hosting this whole space. And we had some really amazing conversations around service meshes. And I know I certainly learned a lot of new things. And I hope our audience also had some great takeaways. So let's have some more great conversations in future and learn more about various networking topics. And we would love if you could share a thread or write a blog about your learnings. And over to you, Marino. I really had a great time. Thanks
Awesome.
for
Yeah.
inviting me.
Yeah. Thank you so much for hosting this. We'll probably do this again in a couple of weeks, and we'll change up the topic and maybe focus in on container networking a little bit more, or maybe some automation. There are a few topics that Akansha and I have been debating, and we really want to just make sure that we're giving you the full gamut of application networking through this series. So again, thank you everyone for coming by. Really appreciate it. I hope you learned lots today. If you missed the first chunk of it, catch the recording. Akansha gave an amazing overview of what a service mesh is, and that's a great starting point for us to dive deeper into some of the specifics. So again, take care everyone. We hope to see you again soon. I wish you the best today. Take care. See ya.
Bye, everyone. Take care.